Yeah, it's my great pleasure to introduce David Sonntag as our first speaker of this session. And actually, I first met him in New York when we were both with NYU still. I now noticed that you are now with MIT as an assistant professor. And yeah, already when I was with NYU, I was very impressed by how he applies very interesting, innovative machine learning techniques to a domain that we probably now or at some point care about, and that is healthcare. And yeah, I'm looking forward to see what you're working on these days.
Well, thanks very much for the organizers for inviting me. In fact, they didn't invite me. They invited Anna Karamanska to give this talk. They invited me to give another talk, but Anna unfortunately couldn't make it today. She has a young baby at home. And so today I'll be taking her place to talk about this work. It's joint work between myself, Yassine Jernait, who was a PhD student of mine at NYU, and Anna Karamanska, and really Yassine did the chunk of these slides. He couldn't make it either, but really the credit should go to him. And this work had appeared in our ICML 2017 paper. So the high-level question is as follows. How can we do extreme classification quickly? Right? This is the topic which has been discussed already quite a bit this morning. And for us, we've been very much motivated by language modeling. Although the techniques I'll tell you about today will be really applicable to many other settings, such as classification. So in language modeling, we would like, given some text, to learn a distribution over text such that we could model, for example, draw a new sentence from the model, or we could ask, given some existing words, what's the likelihood of seeing some of the next word? So let's look at this simple example here. The rat scared the cat. So if we had just seen the first 4 words, the rat scared the, we might ask, what is the likelihood of the next word in that sentence, in this case, cat? Well, by the chain rule, any set of words, W1 through Wn, the distribution over them could be factorized as the probability of word 1, probability of word 2 given word 1, probability of word 3 given word 1, comma word 2, and so on, just by the chain rule. So in order to compute that each conditional likelihood, we need to get some distribution over the next word given all the previous words. Neural language models typically summarize those previous words with some context vector. In this case, we'll refer to it as v context. And it might, for example, be done by taking word embeddings for each of the words in the sentence, pushing them through a recurrent neural network, and looking at the hidden state at the last word, which in this case is the. And that would summarize all of the previous words in some d-dimensional vector. And given that d-dimensional vector, then the question is, okay, what is that next word? So we want to predict one class out of a class of size the whole vocabulary, which could be in the millions. Now, often that conditional distribution of that last word, P of cat, given the context, V, the rat scared the, would be parameterized with a softmax function. So it would look something like this, where we say that for every word in the vocabulary, we have some vector. So that's here denoted as UW, which is also d-dimensional. And then the conditional distribution of W given the context is just given to you by a renormalization of the exponential dot product of the context with that word vector, UW, renormalized so that we have a valid distribution over all possible words. And this is nothing new. This is the standard approach to language modeling that's used across natural language processing. Now, to compute that numerator, for example, that exponential term, it takes running time order d, where d is the dimensionality of that context and word embedding. But in order to compute the full conditional distribution, we need that denominator as well. Right? So it's going to be order d time to compute each of these terms, and then the denominator is going to be order d times v, the vocabulary size running time, because we have to sum over all possible words in the vocabulary to get a valid distribution over the vocabulary. And that's the problem, right? So that ends up being one of the main bottlenecks for learning neural language models. So there have been a number of approaches in the NLP community for trying to address this bottleneck during training. You might have heard of things like negative sampling, self-normalizing models, and hierarchical softmax. And in our work, we're going to be focused on that last approach, hierarchical softmax. And one of the really nice things about this hierarchical softmax is that it gives us a valid language model, so we can exactly compute the probability of any next word in the sentence. And it's going to be fast, not just at training, but also at test time, that some of the other approaches might not have. So what is this hierarchical softmax that I'm talking about? Well, the key idea is rather than describing the distribution over all of the words using a softmax, we're going to predict first, we're going to, in essence, follow the trajectory through a tree, and only when we get to the leaf of the tree will we know what is the word that we want to predict. And at each step, we're going to be just making binary, or in our work, it'll be m-ary decisions. And so the total running time in order to make a prediction is going to be much smaller than the vocabulary size, potentially logarithmic in the vocabulary size. So let's see how this works. So let's stick with the previous example. We want to figure out, given that context, what is the likelihood of the next word being cat? Well, the first thing we're going to do is we're going to look at the root of the tree, and we're going to ask, what is the likelihood of branching? In this case, it's a three-area tree. So what's the likelihood of branching to N2 as being the next step in this procedure? And I'm going to be asking about each one of these steps until you get to the leaf corresponding to the label cat. So we're going to factorize, we're going to stipulate that the distribution of cat given the context is now going to be factorized as each decision that has to be made to get to that leaf. So first probability of N2 given N1, then probability of N4 given N2, then probability of cat given N4. And if you multiply each of those probabilities together, you get to the overall likelihood of getting to the label cat. And you can now imagine a generative process where if we want to sample a new word given this conditional context, we're going to sample from that first distribution and sort of work our way through that tree till we get to the leaf. So the running time then goes from, at each decision, it takes running time d times m, where m is, again, the branching factor of this tree. D is the dimensionality of the context. And if the tree is of depth log v, the vocabulary size, meaning it's a balanced tree, then the running time is now logarithmic in the vocabulary size in order to sample from the conditional distribution or to estimate the conditional likelihood of a particular label. In this case, the label, again, corresponds to a word in the vocabulary. So this hierarchical softmax is widely used in NLP, but the question which everyone in the community always asks is, what should that tree be? What is its structure? Where is it coming from? And there have been a number of approaches to try to address that question. The first one has been one of clustering. So, for example, you might use off-the-shelf algorithm like word2vec to learn some word embeddings and then do some clustering of these word embeddings to get a candidate tree and then train the parameters of that tree. Or maybe iterate this procedure in some way in order to try to find trees that are semantically meaningful, that words that might be words that might have similar meanings maybe are in similar locations along the bottom of the tree. So that's one approach. Another approach that's widely used is based on Huffman coding, which is completely wacky, except that it works. So this Huffman coding idea says that we're going to completely ignore the semantics of what these labels are. We're just going to try to learn a tree structure such that very frequent labels, and this won't be a balanced tree, very frequently occurring labels are high up in the tree and not so frequently occurring labels are low in the tree, so that if you were to completely ignore the context and just ask the question of what's the expected number of branches you need to do to get to a word, it's sort of as low as possible. And finally, in even more recent work, for example, we've used this in my own lab. People have just gone for random hierarchies. So just giving up on anything and just saying, okay, we're going to randomly create a tree. So for example, in my work, I've used sort of a square root V tree where we have a square root V branching and then it's not very deep. And so we just randomly assign words to the leaves and learn a model, and that also seems to work reasonably well. But this leaves open the question of, okay, these things all work reasonably well, but what is there still to be gained, right? If we were to actually try to think hard about this problem and learn that tree structure, could we do better? And this is one of the first works to really address that problem. And the conclusion, I'll just tell you that now, the conclusion is that there is a gap in performance, a substantial gap in performance between either the clustering-based approaches or the Huffman coding-based approaches and the flat softmax. And by cleverly learning that tree structure, we completely eliminate that gap. That's the conclusion, while still attaining most of the computational speedups. So how do we get there? Well, there's been quite a bit of earlier work on learning tree structures in similar settings, notably by Karamanska and John Langford sitting here. And that itself built on even earlier work by Kearns and Mansour. But they considered settings where there was no, where the contexts were unchanging. So for example, if you think about a typical bag of words classification setting where we have a fixed feature vector representation, we're just trying to learn how to predict from a large number of classes what the class should be, then those algorithms would apply. But here the story is a little bit different, because remember, when you're learning a language model, you're not just learning this tree structure but you're also learning the recurrent neural network parameters as well, right? So you have to learn the word embeddings, you have to learn the parameters of your gates, and so on. And so what that means is that the representation of your contexts are changing as well during your learning algorithm. And what we don't want to do is a two-step algorithm where you fix the representation and learn the tree and then alternate. What we want to ask in this work is there a way to jointly learn everything? And so we're going to give an algorithm to do so. We're going to provide very weak theoretical guarantees. So we have some theory in our paper, but really it leaves a lot to be desired. But we do show that this works very well in practice. And we're going to evaluate this in both a language modeling setting and in an extreme classification setting. So our overall approach will actually be a little bit similar to how you would tackle learning a decision tree. Right? So if you think about learning a decision tree, you might think about some criteria for how you would build that decision tree. You think about things like purity or accuracy as measures for how to choose the next split, and you might build that decision tree in a top-down fashion. We're going to give you the same sort of objective here, except it's going to be a little bit different to take into consideration some of the subtleties of this problem. And our learning algorithm won't be a greedy top-down algorithm. It's going to have steps in it of fitting the language model, completely redoing the tree, and alternating. And what we're going to show is that using this objective leads to good trees. So here's now where I get into some of the details. So first, I never really told you how we branch. So let's first look at the setting of just two classes. We'll call it the class for the word lost and the one for time. Suppose we have some data, where here the data consists of sentences that give you relevant context for which you would like to predict that next word, and let's suppose that next word was lost or time. So if we just had two classes, then our tree is just going to be a binary tree of depth 1. where we only have to make one decision, go left or go right, in order to get to one of these two classes. And so there, one could use just a sigmoid function where you take that context and you hit it with this linear classifier parameterized by a weight vector h, and that gives you some distribution according to the sigmoid or logistic over which class is the right class for that context. And if you had more than two classes, that is to say, if rather than a binary, this were an m-ary tree, then you would just use a softmax instead. And so then that can give you the probability. Then gives you the probability of each one of these classes given the relevant context. So now suppose that you have more than two classes. And again, for this example, I'm going to stick with m equals 2, so a binary tree. But in our experiments, would go with m up to 65. So now the story is going to be as follows. Consider the following data point. I ate some, gives you some context. This is how we do prediction. So not learning, but just prediction, supposing that we have a learned model. We start at the root. The root node is associated with some parameters. In this case, since it's a binary tree, there's just a single hyperplane. We're using linear splits. And that hyperplane tells us, by taking the dot product of the hyperplane with that context vector, it decides to go left or go right. Then here, let's say you go left. You make the similar decision now for node n2, node n4, and eventually you get to your prediction, which is the label pi. Right? So then the likelihood of pi is just given to you by the product of each one of those softmaxes of the decisions needed to make to reach that label. So now let's ask the question of how do we learn that tree structure? Well, we gave an objective function which will quantify how good the split at any one node is. And then our overall objective function is going to be the sum of those per node objectives. So now I'll tell you what each of those per node objectives is. For each node n in your tree, and again, this is an m-ary tree with k overall classes, where k, remember, could be something like if this was a vocabulary, it would be your vocabulary size. So for each node in the tree, we're going to look to see, first, what are the distribution of classes that reach that node in the tree? Right? So if you were to imagine prediction, where each data point sort of follows its way down, in this case, we're going to look at the path from the root to the leaf corresponding to the correct label for that data point's class. And so we're going to look at all of the data points that reach some corresponding intermediate node along the path from the root to its correct label. And that will give you the distribution Qi. And obviously, if this distribution Qi is very peaked to one class, then you're basically there. You basically know what the right class is. And if this is something like a uniform distribution, then you're very uncertain. And your goal here, of course, just like with learning any type of decision tree, is to make this be as peaked as possible, meaning you're making progress towards figuring out what the right class is. And so in this example here, we have 4 classes, and for example, this might be the root, and then we say this Q just gives us the distribution of data points that reached that corresponding node with that class. Now the next quantity of relevance is going to be measuring, now that you know which nodes with which examples with what labels reach this node, where are they sent to next, right? Which child is it going to? And that's going to be essential for characterizing how good is the split at this node. And for this, we're going to measure that by this conditional distribution, P of j given I, where we're conditioning on examples of each class I. So we're going to just look at data points of some class, and then ask, what is the distribution of data points of that class that go to each child? And intuitively, again, we want this to be, we want each of these conditional distributions to be as peaked as possible, which means that we're sort of routing the data points in an optimal way. And here, where we're using a softmax to make those routing decisions, this is just given to you by the following expectation. And finally, we can put those two pieces together, P of j given I and Q of I, to get P of j, which is simply the average, the fraction of examples that go to child I of this corresponding node. Now, this is just a summary of the three definitions I gave you. And using those three definitions now, we have our overall objective, which is given on the very bottom here. So the objective for node n is a sum over the qi, where again qi is summing over all possible classes or labels. And then a sum over the children of that node of pj minus pj given I, right? And so we want this to be as high as possible, where as high as possible means sort of this average quantity. We would like all of that mass to be routed towards a single child for each class. Now, this has a number of properties. So, for example, what one can show is one could define this notion of purity, alpha n, and one can show that this objective function correlates with good purity. Namely, that if you were to maximize this objective as much as possible, it would lead toward splits that are pure. Moreover, one could characterize another notion of balance. How much are we balancing across sort of the classes along the tree? And once again, one can show that you have to maximize this objective as much as possible. It also leads to good balance. So in our paper, we have some theoretical results which motivate those two properties I just gave. And also show that if you were to that there exist trees that are not too large that satisfy these properties. So our overall learning algorithm is then as follows. We're going to have, this is going to be a batch SGD algorithm. And for each batch size of examples, we're going to completely redo the tree structure. And we're going to we have a greedy algorithm which chooses the new tree structure, that is to say, relabeling each of the leaves with new classes, that we show is greedily maximizing the derivative of the sum of these node objectives with respect to our model parameters, subject to well-forming constraints. And so for each batch, we're going to first completely redo the tree structure. Then we're going to take gradient steps with respect to the model parameters, so that recurrent neural network, the word embeddings, and also the split parameters. Now, importantly, each one of these steps, both choosing the new tree structure and model optimizing the parameters of your language model, are all optimizing the same objective function. And so that really starts to get at this goal of having a unified objective that deals with both the fact that the representations are changing and the fact that we want to find really good trees. So here's an example of what it looks like. Suppose we see a new example for this class was. We figure out we look in the current tree to see what leaf it's at. We compute the gradient of this objective for every node along the path from the root to its true label. We can update node statistics. We take a gradient step. And then we update the tree structure. And so here you'll see a sort of global change like this, where pi moves from the far right-hand side. We do a new split, we get this new tree structure, and we iterate. So in just the remaining 2 minutes, I'm going to talk a bit about how this algorithm does in practice. So first we looked at a language modeling problem where we took a large corpora from the Gutenberg project, 50 million word corpus, We use a vocabulary of size 250,000, so there are 250,000 classes here we're trying to predict. And for this work, we used a really simple log bilinear n-gram neural language model. We learned a m equals 65 array tree of depth 3. And what I'm showing here is a little bit hard to see, but what I'm showing is the tree structure that's learned and visualized in terms of what are the classes, the most frequent classes that are underneath each node of the tree, to try to get a sense of whether we're actually learning, whether there's any interesting semantic grouping of the classes that's learned by this algorithm. And indeed we see that. So for example, on the far right, we see that the classes this, these, those, and so on are grouped together. Over here we see the classes put, set, lay, cut are grouped together, and so on. But more importantly than the semantics is really how it does in practice. It's a real shame that these plots aren't showing, but I'll walk you through what they're saying. This plot on the left is the x-axis is epochs of training, and the y-axis is perplexity or held out a measure of held out likelihood, and which we want to be as small as possible. So this red line that you see up here is the held out perplexity of using a random tree. This blue line that you can see pretty clearly is the held out perplexity of using a flat softmax. So it's going to be much slower to train and use a test time because of the fact that it's not hierarchically structured. And you see that there exists a pretty big gap there. Although I'm not showing you it here, the clustering tree type of approach is actually worse than all of these lines. Now the green line, which is almost impossible to see, I'm going to show you it by following my cursor. It initially begins by somewhat being similar to the random hierarchy until roughly the second epoch of training, where it settles on a good tree structure. And from there on out, its learning curve is identical to that of the flat softmax. And so what we see here is that by learning the tree structure, in fact, we're able to fully recover the quality of model that we're able to get using just a flat softmax. Next, we looked at a text classification problem where we actually modeled it almost identically to the density estimation setting previously considered, with the only difference being that here, to do prediction, we don't want to sample, we actually want to do map inference. So for prediction here, we're going to be doing a map inference for the class, which we do by a simple branch and bound with a depth first search through this hierarchical tree in order to predict for each new example. We evaluated it on this Flickr tag classification setting, where the input is an image like this, and your goal is to figure out sort of what are the tags that this input corresponds to. Now, most people use this data set to try to predict the tags directly from the image or to do something about relating the image to the caption. I want to first point out that we could have used this approach from the image itself, right? So one could imagine using our algorithm to simultaneously learn the parameters of a convolutional neural network and a hierarchical softmax to predict the class. That would be a good use case. We wanted to stick with language because this is something that my student is more interested in. So we didn't actually use the image itself. Rather, we used the text of the caption and asked we predict the labels, the tags, from the text of the caption. Using a simple bag of words embedding, where we're simultaneously learning the word embeddings at the same time. And indeed, the same story applies here, where the learned tree that I'm showing you here for the areas 5 and 20, obtains precision at 1, which is substantially better than you could have gotten with a Huffman tree or a couple of the other baseline algorithms that we compared to. What's particularly interesting, however, is that as the dimensionality of your word embeddings increases, that gap seems to shrink. So I think that's something that would be interesting for us to think about in the future. Right? In particular, what this motivates is that maybe this approach of learning hierarchical softmax, where learning the structure, maybe that's most important in settings where you're more resource constrained, where you can't afford to have very large vocabularies. And so the decisions that are, you can't afford to have very large dimensionalities. And so the decisions that are made at each step of the tree are hard. And because they're hard, learning the tree structure is more important. So I'll just conclude by saying this is one of the first works to show how to learn the tree structure of a hierarchical softmax together with the underlying representations. There are a ton of open questions, particularly on the theoretical side. And there are also some interesting empirical work to be done and some new directions there. So just to spur some interest, there's really no reason why we had to use a tree structured model. One could imagine using a forest. One could imagine allowing each class to appear a couple of times rather than just once in the tree. And one could even imagine using the same sort of structure learning algorithm for other deep learning applications. So thank you.
Okay, thank you. So we have maybe time only for one or two quick questions, if there are any. Yeah, maybe this one, and then, yeah.
Do you have suggestions of applying hierarchical softmax in the context of multi-label classification?
So the question's about applying hierarchical softmax for multi-label classification. Oh, naively, this could be used there as well. I don't know of the best way to do it. I had to think about it. That's a really interesting question. So David's asking whether the structure could be reused. Well, one of our original thoughts is that the structure itself might be interesting from a linguistic point of view, particularly in a language modeling setting. I don't think there's evidence from our experimental results to justify that statement. A second question is whether the structure could be reused for other predictive problems. And I think the short answer is yes, if the way that the representations relate to the labels that you're predicting is generalizable.
Okay, let's thank our speaker.
So,
Okay.